Hello guys, welcome. In today's video, I'm going to talk about what's going on in the code of the exhaust arm. But before the code comes the algorithm, the thought, the idea, the architecture. Having that is really helpful. This is literally a map that keeps you from getting lost when you're coding or even testing your system. And as you can see here, I have my main functions in blue: rearming, disarming, arming, and the dragon crest. So, and these are the conditions. So initially I am in the rearming state, then if I hit the reset button or if I power on the device, it's gonna disarm. And then if I place my hand, it's gonna close. If I contract my muscle, it's gonna get into the arming state. If I don't, it's gonna open. And if I still have my hand, it's gonna close and open. We're gonna stay in this kind of loop here until I contract my muscle and completely arm the device. And if the device is open for a certain amount of time, it's gonna go back to the rearmed state. And here, if I'm in the if it's in the arming or the armed state, and if I contract my muscle once again, I'm gonna turn on the LED corresponding to the dragon crest function. And when my device is in the arming state, if I hit the reset button, it's gonna get disarmed and I will be able to remove my hand. So that's pretty much what's going on uh, in the exhaust arm. And you see, I mean, for the sake of the video, I really made this good looking uh, workflow chart, whatever you want to call it. But when I was making the project, I really used that. I have a lot of sketches like that. So this is the code. In this video, I'm going to talk only about what I call the base mode, which is when I am generating the PWM signals to control the servos only with my microcontroller. I have another mode, I'm going to talk about that in the next video, the I2C mode, where I'm using the PCA9685 to control the servos. So here's just my enum that defines the two different modes. And here are the values of the angles of my motors. These are some flags I'm using. This is for the PCA, so not in this not for this video, but this is the, how can I say, yeah, it's the status of the I2C, and this allows me to automatically switch from one mode to another. If we go here, I have initially I am in base mode. So if on the receiving end I have an OKRX, which means that the PCA9685 is responding, then I'll go from the base mode to I2C mode. And if that's not the case, I will remain in base mode. And as you can see here, if I'm in I2C, I'm going to call disarming I2C. And if not, I'm going to call the basic disarming function. So here I have my switch in base mode. I mean, it's pretty much the same thing between I2C and base mode. So here I have a wait time, which is, I mean, I do that with the how-get-tick function, which is equivalent to the millis of the Arduino. So here I just waiting for some time. I have a photo resistance here. So if I have my hand or not, and this is the position of one of my motors. So if all these conditions are true, then I'm gonna close the device, and if I contract my muscle, then I'm gonna get into the arming state. And if I don't, here's the loop that makes it open and close all the time. And after some time, after 20 seconds, if nothing happened, so if I didn't put my arm contracted the muscle, my muscle, then I'll go back into the rearming state. And I have another function here that's just to check the level of the battery, the battery of my electromyogram. If it's under a certain value, then I'll have an LED that will blink to indicate that the battery is low. Here are the two functions that I use to convert the angle into the corresponding compare register. So this is for up counting and this is up down counting. The value of the capture compare register when you're in up counting is given, the duty cycle is given by this formula. You have the capture compare register plus 1 divided by the auto reload register plus 1. And when you're in up down counting, it's only capture compare register divided by auto reload register. I talk a lot about these things in my first software video, the capturing frequency of a signal. It's in the description if you're interested in that. But here I'm going to detail the PWM a little bit more. So this is the generic formula of the duty cycle. Now, if you want the capture compare register, you're just going to do duty cycle times auto reload register minus 1 in up counting, which is the formula given here. So this corresponds, give me a second. So here, when you have a servo motor, usually 0 degrees corresponds to 1 milliseconds, 90 to 1.5 milliseconds, and 180 degrees corresponds to 2 milliseconds. And this is the frequency, 20 milliseconds or 50 hertz. So these little servos work with a frequency of 50 hertz. And the PWM is just the ratio between uh, this value divided by this one. It's a percentage. So this is the maximum value, the frequency, and this is the given milliseconds that correspond to an angle. And as you can see in this configuration here, for every 90 degrees, we have plus 0.5. So from 0 to 90, we go from 1 to 1.5, and from 90 to 180, 1.5 to 2. So we also have plus 0.5. So for 1 degree, it's going to be 0.5 milliseconds divided by 90, which gives you 0.0055. So this is actually the duty cycle. The plus 1 here is for when you have 0 degree, because if you have 0 here, you just have 1 divided by 20, which corresponds to the 0 degree. You may also have some servos that are 0.5, 1.5, and 2.5. The principle is exactly the same. So, the formula is it's the same thing, but for my servos, I think they really work with the classic uh, 1 millisecond, 1.5, 2 milliseconds. So based on that, I have my duty cycle here. This is the auto reload register of my counter, of my timer, beg your pardon, which we can see here in the definition of my timer here. My auto reload register is 10,000 minus 1, so 99.99, with the plus 1 is just 10,000 here. So we go back to this formula where you have capture compare register is equal to duty cycle, which is this value, times auto reload register plus 1, which is 10,000, minus 1. And this allows me to directly use angles instead of thinking of what is going to be the value of my compare register. And I do the same thing here with up down counting. Now I'm using up down counting because I have a continuous rotation servo, and the continuous rotation servos are a little bit more difficult. I mean, they need more precision, so that's the reason why I'm using up down counting, because I have a little bit more accuracy with up down counting. And given this formula, the auto reload register is gonna be 20,000, because the formula of the frequency is the clock frequency divided by prescaler times auto reload register times 2. So if you do, my clock is 8 megahertz. I mean, let's go into the definition quickly of timer 3. So I have an 8 megahertz clock, I have a prescaler of 4, and I have an auto reload register of 20. And the given frequency is gonna be 8 megahertz divided by 4 times 20,000 times 2. So it's gonna be 8 megahertz divided by 160,000, which gives me 50 hertz. So I still have my 50 hertz for the servo. So the formula is pretty much the same, and based on this, I just multiply uh, the duty cycle times the auto reload register. And this allows me to control all my servos based on the values I have. So for example, if we get into the rearming, here I have my capture compare register, and I call, the return value of my function of the up down counting reg ud, and I put the value of the angle here, and the function is going to do the conversion. Here's my conversion callback function. For those who've watched my DMA video, I think you can recognize this, because I'm using two channels, two ADC channels. Here, one for the photoresistor to determine if I have placed my hand or not, and this is for the battery level of my EMG. I will make the code available on my GitHub after the next video on I2C.